Well, hi guys, it's Mr. T here at my virtual beach. Anyway, it's you get a bigger picture or a different one, but it's what I got. Just a little fun. But what we're really going to be doing here is talking about the SAVVAS book on topic 5 and section 6, and this is called inverse relations and functions. So last section we talked about using the function notation and composition of functions, and that's going to come in for today. For today, it says I can represent the inverse of a relation using tables, graphs, and equations. And the essential question is, how can you find the inverse of a function and verify the two functions are inverses? So that's what we're trying to get accomplished today. So let's look at our first example here. All right, and then maybe that'll be a good spot for me to hang out. All right, so example 1 says represent the inverse of a relation. Okay, so this is a table, and you used to have an equation that goes with the table, but this is just a table of ordered pairs, and you're not worried about the equation that goes with it right now. The point is, what is the inverse of the relation represented in the table? Okay, what is the inverse? Well, let's talk about this first. This table represents some sort of relationship that these are connected together. The x is independent and the y is called dependent because it depends on what the x is, on what the y is going to be. What you plug in, what's going to be output. So independent and dependent. Okay. And so it says recall that a relation is any set of ordered pairs x, y, where x is the independent variable and y is the dependent variable. An inverse relation is formed by the roles of independent and dependent variables are reversed. So here's the original that we have here, and you see all these are red. Okay, and now what we're going to do, this is relation is a function. Well, let's come back to that. We're going to switch it up. So all the y's are going to turn to x's, and all the x's are going to turn to y's. Switch x and y. That's the fundamental behind inverses. Switching x and y. That's the fundamental concept for inverses, okay? We can do that in all kinds of fancy ways, but ultimately, if you switch up an equation or switch up a graph, the x's and y's are going to be switching places. All right, so let's come back over here. It says that this right here relation is a function. Okay, now a function says it's got this one-to-one relationship, but basically what we're saying here is none of the x's are repeated. We don't really care about the y's. So this is a function because none of the x's all the x's get used one time. Now when we reverse it, can we still say that the inverse is also a function? Well, what they did is they rearranged it and said, no, look at that. The one is used twice. So let's go back over this. Here's the original relation. This is the inverse relation. And that's just a fact. Now, because the inverse uses this one twice now, the inverse can't be called a function. So the original was called a function, but this one does not fit the definition. Does that mean they're not inverses anymore? No, they're still inverses. It's just that the second one does not fit the definition of function because these ones were repeated here. Okay? And that's what it's saying in all these little bubbles here. Okay? Now, we switched the x and y's, and we saw the reordered the pairs because just notice that this issue was happening. So if an inverse relation is a function, f, it is itself a function. It is called the inverse function. And we use that by using this notation here, okay? So if we can call this relation function f, okay? So if we can call this relation function f, and we do the inverse, and it turns out to be a function too, we're going to label this the inverse function of x. Okay? But is that okay to do? No, that's not okay to do because this was what? Not a function. But if it was, that is how we would use to identify it. Okay? Okay. Now here's a try it. It says identify the inverse relationship. So what means switch x and y. So that's what we're going to do. We're going to take, let's see here. The examples had all the x's in red. So what we're going to do is we're going to bring them, all the x's are going to turn to y's now. So that's -1, 0, 1, 2, 3, 4. And the other was blue. Okay. And so the y's are now going to be x's, 9, 7, 5, 3, 1, -1. Okay. So this box shows, since we reversed these two, this is the inverse. Okay. This is the inverse relation. That's the fundamental to an inverse. Now, separate question. Okay. Is the original relationship and function? Well, did any of the x's use twice? No. So this is a function. Okay. So function. Separate question. Yes. Did any of these get used twice? No. So this is also a function. Now we're going to talk about the vertical line test when it comes to a graph, but right now we're just talking about the ordered pairs. So it turns out that this would be called f of x. And since this is also a function, we would label this name f to the -1x. Okay. All right. Let's check out example 2 now. Okay. With example 2, it says find an equation of an inverse relation. So how do we do that algebraically? How are we going to do that algebraically? Well, let me bring in a little tool here that might help us. Where is it? Okay. Let's just open this up a little bit at a time. So, well, the first thing we're going to do, if you'll notice, is take the f of x and put y in its place. That worked. We're used to doing that. So that's the first thing that happened. And then the next thing it says, switch the roles of x and y. So literally, what has happened? It doesn't, apparently it's not going to do that. It's going to switch the x and the y. Did the square get moved? No, just the x and y got moved. And then now they want you to solve for y. So what do you do to solve for y? What's the opposite of squaring? That's square root. What you do to one side, you do to the other. And so that gives you the y, and this gives you the plus or minus x. So this is the inverse of this up here. Okay, but you notice they did not use the f to the -1x. And they said, be careful about using that label. Be careful about using that label because oh, that's interesting. That's not really what I was looking for. Okay, we'll stay with that. Because we got to know, yes, this is the inverse, but does it fit the definition of a function? And this one is not going to. So just to remind you, that is the notation. So then it says the inverse of f can be represented algebraically by y equals plus or minus square root of x. Okay. And then here I am again. All right. So that's how you do it algebraically. Get caught up in my book over here. Now we're going to look at how this looks like on a graph and how can we identify this on a graph. So it says Find the equation of an inverse relation. Okay, how are the graphs of these two, the original function and its inverse, okay, how are they related? Okay, well, the original graph is, let's get rid of this. So the original graph is this guy here, right? And so that's that parabola. It's the parent function, actually. Okay, so that's the original. And then when we graph this positive square root of x, you get the top piece, right? And then the bottom piece will be the negative part. So what do you see happening here? If I took, and this is the y equals x line. If I was to fold this like a piece of paper, that would be symmetric, right? So that's how you can physically or visually see that they are inverses. So if you can take the original and everything flips over, the y equals x line, then you have inverses, okay? So these are the graphs of the inverses. Now, again, different question. Is the original equation a function? Yes. Now, what I'm going to do is something called the vertical line test, okay? I'll try yellow. See, can we see yellow? Let's go a bit thicker than you might. Oh, it's too thick. Okay. So what we do with the vertical line test is we pass it along. And so I say, if this vertical line touches the graph more than one place, so we're talking about the blue one. So no, as I go along, it only touches in one place. Now, how does that work? Well, vertical line test works because if it touched the line twice, that means the x was used twice, and we can only use our x's once. So the vertical line test says, hey, okay, the original is a function because it only touches once. But now let's try the vertical line test. Oops, let's not do that. Okay, how about the red, the inverse? Well, immediately, what do you see? Well, 1, 1, and 1, negative 1. So the positive 1x was used twice. So that means the inverse is not a function. It failed the vertical line test. Now, here's something interesting. So it's the same picture. Do we even have to draw the inverse to check that on the graph? No, it's something, they got something called a horizontal line test, okay? A horizontal line test. So you take a horizontal line, and what happens is this. If I plug it right here at the 1, is that not exactly the same thing as if you took and flipped it, wouldn't that turn into the yellow line? So what they're saying with the horizontal line test, okay, let me back up. A vertical line test, let's get this guy over here. Okay. With the vertical line test, it tests the current function. So if all I had was the blue parabola, I'm testing it with the vertical line. But I'm too lazy to draw the red parabola or sideways parabola, okay? So what I'm going to do is I'm going to take this horizontal line, and I said, now if it fails the horizontal line test, that means the inverse won't be a function. That's the case. So some of y'all, that makes a lot of sense to you real quick and easy, and it works, and it really works for you. Some of you, you're just going to have to draw the inverse and just always use the vertical line test. And at some point, the horizontal thing might click for you. That's all we're going to do for the moment, because that's not an absolute necessity. All right, so let's finish up what they're talking about down here. It says the graph of the inverse of f is the reflection of the graph of the y equals x squared across the y equals x line. So we already said that. let's leave that be. It'll bring up the next thing. So now it says, let f of x equal 2x plus 1. Write an equation to represent the inverse of the f. Okay, so I'm going to give you just a second here and see if you could do this for yourself. So you need to pause it. Okay, let's see if you agree with me, okay? So the step one was to rewrite the problem with y. That was step one. Step two was to switch the x and the y. So that means I'm going to put an x here and a y here, and everything else is going to stay exactly the same. And then lastly, okay, now officially we switch the x and y, so this is actually the inverse, but it's customary to solve it for y now, okay? So I'm going to subtract 1 from both sides, put it over here, not even underneath it, so I don't, because they're not like terms. So that ends up being x minus 1 right here equals 2y. And then I'm going to divide everything by 2. And then that leaves me with x minus 1 over 2 equals y. Okay, so this is the inverse. Okay, that's what we did. We found the inverse of the original function. Good for us. Now, how can you use a graph to determine if the inverse of the original function is also a function? So that's where we got to here. So I went into Desmos and I went ahead and did that for time purposes. So the blue line in this case was the original and the red line is the inverse. Now again, you see this y equals x line, and I strongly encourage you to, when you're doing this, to put that in so it's much easier to see the symmetry. Are these two symmetric? Do they reflect over this line? Yes, they do. So yes, these are inverses. Okay, you can see it graphically. Okay, so our task was what? Find an equation of an inverse relation. And so we've done that plus more. Okay, second one, restrict the domain to produce an inverse function. So what are we talking about here? Well, over here we said the blue is a function, but the red is not. Could we restrict something? Could we not use the whole thing and then that would make things work out for us, is what we're talking about. Okay, so we're saying here, this is all good. So consider again the original parent function here with a domain. Under what domain will the inverse relation be a function? So remember that horizontal line test? What do I need to do in order for this not to happen anymore? Okay, so it's fine. I don't care about that. But if I turn it sideways, and that's something you can do, you can almost just turn it sideways and take a look at it and see if it passes the vertical line test. So that's not going to happen. So they're saying here, if we took and got rid of the left-hand side of it, you would only get this right here. Would that work for us? If we only took that for the original and then flipped it over that y equals x line, would they both pass the vertical line test then? Yes, they would. And so it's called restricting the domain. So what is the domain here currently? The domain is currently all real numbers, right? All real numbers. But they're suggesting, let's do something different. Let's say we only use x's that are bigger than or equal to 0. See these over here, or what? 0 comma positive infinity, and that would be equal, okay? They're saying if we only use this domain right here, I think that'll make things better for us. And so here we go. So here's the restricted domain, okay, of x is greater than or equal to 0. And then when we flip that over, we get the positive square root. The positive square root. So we drop off the negative square root and just do the positive. And now everything's great. So we have the blue, which is the original. We flip it over the y equals x line. There's your inverse. And because we didn't do the whole thing on the first one, they're both now inverse functions. And notice that they used this notation, not just y equals. They used the f to the negative 1. That means inverse of f. Okay? So that's how you can see that on a graph. Okay? Now, here's the try it, for example, number 3. Okay, it is 3. Okay? It says find the inverse of each function by identifying an appropriate restriction of its domain. Well, you first have to find the inverse, and then you're going to like, okay, how could I cut off the original so that it will work out better? Okay? So you want to give that a try? You might want to pause it. Okay, well, hopefully you gave that a try on your own. Let's see what I got going on here. Well, I got a little trick to show you. Yes, you're supposed to put a y here for f of x and switch x and y. But let's look at this original problem here. Here's the blue one in decimals here. Here's the original for a. Okay, this is a. Which is that there. It's perfectly fine for a function. Okay. But what I did, but because this, this guy here is the inverse, and that's not going to pass the vertical line test. So the original fails the horizontal line test, which means the inverse will fail the vertical. All right, so how did I get this to graph? Because does that not look like the inverse? It sure does. But that's a problem, okay? Look, it's a problem. This is not going to be a function. So they say, how can I restrict the original's domain? So what we're going to do here is we're going to say, let's cut off that part right there, okay? And if we cut that off, when we flip it over, isn't that going to cut this piece off? Okay, and so this is x is greater than or equal to -4, right? X is greater than or equal to -4, and this is the restriction for this one that makes it everything go better. Now, some of y'all looking over here, and look what I did. In Desmos, you can do this. All I did was take the original and switched out my x's and y's. So I took the x's and put y's and took out the y and put an x. I didn't solve it for y. Remember a while ago, it said you actually found the inverse because Desmos can handle this. So all I did was switch my x's and y's and bam, I found the inverse. Okay? Didn't even have to solve for y, even though that's the customary thing to do, and there'll be situations where you're asked to do that. All right. Okay, let's do a few more examples, basically, and they're going to deal with domain and range. So keep on adding a little more layers to here. So find an equation of an inverse function. Okay, so they're starting with the square root this time. Okay, so the graph shows that no horizontal line intersects the graph in more than one point. So they're basically saying, if you take this guy here, it passes the horizontal line test. And again, the horizontal line test is if it doesn't touch a horizontal line more than one place, that means once you find the inverse, it will also be a function, not just a inverse relation. Okay. When the graph is reflected over the y equals line to produce an inverse, there will be no vertical line that will intersect the graph more than once. Okay. Since the inverse will pass the vertical line test, the inverse relation will be a function. So then they go take it a little bit further. Okay. What are some other things? Well, they took the original and did it algebraically. Okay, algebraically. So we switched X and Y. That's what happened here, right? Switch those two. The X and Y switched places. Everything else stayed exactly the way it was. And then what did they do? How did they get rid of the square root? Well, they squared both sides, right? And that's where that came there. And then we added 2 on both sides. And that's how we came up with y equals x squared plus 2. Okay. And then when they did the inverse there, which was this guy here, they only did half of it, right? Because they're only doing the positive half. And when you look at that on a graph, it says, so the inverse of f of x, square root of x minus 2, which is this guy here, all right? The inverse is this guy here, and we have a restriction, because that's not a whole parabola, is it? We're only using that piece right there. So you can verify this on a graph. So number one, you can find an inverse algebraically by switching x and y, and then generally they want you to solve for y. But you also can determine if two things are inverses by using a graph like this to check it. Now, the graph is not going to create the equation, okay? Even on this one right here, guys. Yes, I created the equation. The graph didn't do it for me, okay? But this may not be the format that your test or whatever has. So what you're going to have to find one that looks the same, okay, on the graph. Okay, here's another example. Find an equation of an inverse function. Ooh, I got this guy here. Well, they take it and they here's the red one. It's a cube root, but it's got a negative in front, so they flipped it over vertically. Okay, but they switched x and y, and then they solved for y and got this down here. And so both the red one passes the vertical line test, and the blue one passes the vertical line test. So this is not only the inverse, but it's the inverse relation, but it is a inverse function because they both, the original and the inverse, pass the vertical line test, which means the x's were used only one time, not more than once. Okay, so that's doing it algebraically and then proving it through the graph. Okay. Then I showed you how, if you got a multiple choice test, how you could just switch the x and y and plug that into Desmos and then plug in the answer choices to see which one matches the one you're looking for. But you still need to be able to do this by hand because you can't always get around that. Right, now example 5. We're going to use composition to verify inverse functions. Okay, this is what we did yesterday in the previous section. We talked about doing composition of functions. And so all this function notation, one of the primary reasons is so that we can verify two things are inverses. Okay, and this is how you do it algebraically, is to verify it. So what is the inverse of this function? So number one, they switched x and y, and then they isolated the y term. Okay, so they subtracted 5 from both sides, and that's how they got that. And then they divided everything by 2, and so they got this guy here. So let me go to the next page here. Yeah. So that's what they did. Okay. I guess I'm not covering anything up at that point. All right, so here's the original. We're going to do things in red for that and things in blue for green. So how can I do this? So what we're going to do is we're going to find f of g of x, and that's the two ways you can write. Some people call that fog. And so what I'm going to suggest is that we're going to put the outside walls up first, the frame of it. So here's the f of x. And f of x is 2x plus 5. But we're not going to keep the x, are we? No. We're going to take the x out, and that is going to be where we put our g of x, right? So what's going to go inside here? What's inside? Well, if this said f of 3, you would put a 3 here. But since it says f of g of x, that means you're going to put g of x here. Well, what does g of x equal? Well, that big thing. So let's rewrite this. Okay. And so 1/2 x minus 5 over 2. So we have got the f of g of x so far. Now we need to simplify it. I always need to simplify it. So let's do distributive property here. Okay, so 2 halves make a whole, so that's just 1x, right? And then 2 times 5 over 2, again, the 2's cancel, and so that gives you minus 5. And then plus 5 is left over. And so that gives us just plain old x. Is that a good thing? Well, we're going to find out. Okay, so let's start again. So this time we're going to put g of f of x. That means we're going to put f inside of g. So let's put our frame up here. And so g is going to be, okay, one more time. Let's do blue, not black. Blue. So g is 1/2. Whoops. That was supposed to be blue, wasn't it? Sorry. Blue. Got my color coordinating off. Yeah, all that was supposed to be blue. Sorry. That's what messed it up. Let's see, that's 1/2 x. And then minus 5 over 2. And so we're putting f of x inside of g. So f of x goes right here. So we're putting f of x inside the g of x. Okay, so that leaves us with 1/2, and then there's going to be the f of x minus 5 over 2. And so the f of x is 2x plus 5. Ooh, that's pretty ugly there. 2x plus 5. Okay. So 1/2 of 2 is just going to be plain old 1. So there's x. Half of 5 over 2 is going to be plus 5 over 2 minus 5 over 2. And then that turns into x again. So they both turn into x. So when you take f of g of x and you get x, and then you reverse it, g of f of x, and you also get x, that is how we know. So since these both give alpha x, that means these two functions, f and g, are inverses. And so oftentimes they take the first one, call it f of x, and the second one g of x. But this g of x now has a new name, okay? Because they're both lines. It's also can be considered the inverse, right? Um, So they are inverses. We've proven it algebraically. Now, how can we confirm that with a graph? Okay. So here's the graphs. So the red is the original function. The blue is the inverse that we came up with using algebra. And there's the y equals x line. So is that symmetric? If you folded it along that green y equals x line, would they be like a butterfly, symmetric? Yes, they would be. So this is how you confirm it by graphing. You can verify it by graphing. So when they say verify, you can verify it by, if you have both of them, you can verify by looking at their graphs, or you can do what? Do f of g of x, and it better come out to x, and then do g of f of x, and that better come out to x. It always comes out to x and x, the same thing, okay? Just like additive inverses always turn into 0 and multiplicative inverses always turn into 1, function inverses always turn into x when you put them into each other like that. So, okay, here's another example here. They're going to walking you through. And so they have f of x is x squared plus 5, and then the inverse of it is the square root of x minus 5. They didn't go through the trouble of showing you how to do that. And they're saying, are these inverses? Well, okay, excuse me. Are these two functions inverses? So we don't know this is an inverse yet. Okay, so we work and put f of g of x and work all that out, and you get this expression here, not x. We do it in reverse again, not x. They're not even the same thing. So that's how we verify it by algebra using composition of functions, okay? But you can also verify or prove by the graph. So here is the red one, here's the original, and then here in blue is the other function, right? Now, they are not, that's, if you fold that along the green dotted line there, that y equals x, they're not going to be symmetrical, are they? So they are not inverses. Okay, here's a couple more. So you can use the composition to determine whether the f of x and g of x are inverses. So they want you to do that whole composition of functions, both one direction and then the other direction, to see if they both give you x. Okay, simplify out to x. Or you could also use your graph. So I'm going to pause just a moment here and let you try that out yourself. Okay, I hope you did try that out by yourself, okay? And you paused it and did it, and now you're going to check to see what I got. Just real quickly here. So the first one was a no, but see, and this is why that y equals x line is so important, because you see that does look symmetric, but it's not symmetric along the y equals x line. So the A would be a no. And then while this is funny looking a little bit, right? It's a cube root, the red one. Is it symmetrical? Yes, it is. So these two are inverses. Okay. So do we use composition of functions to prove that they're inverses? A lot of times we just get the graph and do it that way. On a test like the EOC or maybe the ACT, do they expect you to know that you can use composition of functions and might suggest that you do it or even make you do it because they show you, the process or something? Yeah, that could happen. So you need to understand how it works and why it works. But yeah, the good news is for us, we're going to be able to use Desmos and graphing calculators to help verify that two things are inverses. Okay? And also check to see if the inverse is a function. Okay, last example here. And again, we're talking about rewriting a formula. So we got a sculpture artist is making an ice sculpture of Earth for display. He created a mold that can hold 4.5 liters of ice. That's what it says. Okay, all right. What will the radius of the ice sculpture be if he fills the mold all the way? Well, here's the volume of a sphere. And what they're trying to do is they're wanting you to solve it for R so you can just plug in for the volume kind of thing. So how did they go about doing it? So to get R by itself, 4/3 and pi and the cube got to go. So the first thing they attacked was the 4/3, and so they multiplied both sides by 3/4. So these things go away. And so now you got pi r cubed and then 3/4 v. Okay, then they're going to do what? Well, could divide by pi, but better choice is to multiply by 1/pi on both sides. And that's how the pi got here in the denominator. Okay, and then to get rid of the cube root, you're going to, cube, you're going to cube root it, and you're going to cube root the whole thing. And that's how we get it equal to r. Okay, so that's rewriting a formula. You're definitely going to need to be able to do that in many situations, especially on the test, but in many other situations. All right, so they go on just a little bit further to put a little twist in it for you, okay? Put a little twist in it for you. It says, since a liter is a measure of capacity or volume, it can be expressed using cubic units in length. When you take the cubic root of an expression involving the volume of a cubic in cubic units of length, the units of the result will be in the correct units to describe the length. Well, here's the deal. He said he put 4.5 liters in. It says 1 liter is equal to 1,000 cubic centimeters. So 4.5 is going to be 4.5 times 1,000. Okay. So we're going to take the volume and put 4. So that's what, you got to be able to figure that out. 4,500. Plug that in there. And it does say to use an approximation. Okay. So 3/4, and just plug that whole thing just like you see it. You're not going to put the centimeter cubed in there. That's a unit. But you put that whole thing in your calculator, and it's going to spit out 10.2 once you round it off. Okay. All right. So let's look at this one last thought here. Okay. It says rewriting the equation to show r in terms of v, because that's what happened, instead of v in terms of r, is similar to finding the inverse. In effect, you are exchanging the roles of the dependent and independent variables. Okay, so when you go from this first equation, this first formula, to the second one, the roles of the r and v have switched. But when you're dealing with a formula like this, we don't actually switch them like we talked about with switching x and y. In this situation, we're not going to do that. Okay. And we're basically, and they're saying basically about a 10 centimeter for the diameter. Okay. Well, I think we finally made it to the other end. So is this inverse relations and functions? Can I represent the inverse of a function using tables, graphs, and equations? So we did it by switching ordered pairs, switch x and y on a table. We looked at how you can verify that over the y equals x line on the graph, and then switch x and y, solve for y for our equations. And we showed how you can use how I can find inverse of a function and verify it using two functions or inverses by using composition of functions or showing the symmetry on a graph. Okay. Whew. As always, I hope that's helpful. Bye, y'all.